Yes.
Okay, so if you remember in the last class, we were discussing that how the CF bond is the strongest and how the CI bond is the weakest. So this nucleophilic substitution reactions, it is fastest in case of iodoalkanes because it is easy to leave the iodine, but it is slowest in case of fluoroalkanes. Okay, so you can here remember that note that the CI bond it is weakest, so it is broken easily. When the CI bond break, it form an I minus during the substitution reaction. The bond breaks heterolytically. Why? Because it is a non-polar atom. It breaks heterolytically with the iodine atom taking both the electrons in the CI bond. So I hope you know both the electrons of this are transferred to this iodine. So it is a heterolytic cleavage. So it is shown by the in this equation. This is iodoethane. So OH minus as a nucleophile comes, okay, and it attacks here, and iodine as a leaving group it leaves. So this is the reaction. So have we discussed this yesterday, or you want to write it?
I don't think we discussed this part.
Okay. So the trend in the reactivity of halogenoalkanes, it is shown below. Like fluoroalkanes is the least reactive and iodoalkanes is the most reactive. Okay, depending on the bond energy. Fluoroalkanes is the least reactive and the iodoalkanes is the most reactive. With alkanes, with halogens. Write it down.
I'm done. I'm also done.
Okay. Next is the substitution with the cyanide ions in ethanol as a solvent. So in this reaction, nucleophile is cyanide ion. To carry out the reaction, solution of potassium cyanide in ethanol, which is also known as ethanolic solution of potassium cyanide, it is made up. This is then heated under reflux with the halogenoalkane. So what happens in the same reaction? In this case, your nucleophile is OH minus, but in this case, your nucleophile is cyanide ion. So same reaction occurs. Cyanide ion, it will attack to this, and this bromine will leave. So we have a propane nitride plus Br minus as the leaving group. So notice that you can notice here we have how many carbon atoms? 2 carbon atoms. Here we have how many carbon atoms? 3 carbon atoms. So cyanide ion, it adds an extra carbon atom to the original halogen-alkane carbon chain. So this is also known as step-up reaction. In step-up reaction, your number of carbon atoms increases by 1. So bromoethane is converted into propane nitride. Ethane is converted into propane with the cyanide. So this question will end up in your exam, that which is in which reaction number of carbon atom increases by 1. So this is the substitution of halogenoalkane with cyanide ions.
I'm done. I'm also done.
Next reaction is substitution with ammonia in ethanol. So if we heat a halogenoalkane with an excess of ammonia dissolved in ethanol under pressure, amine is formed. Amine is NH2. This group is known as amine group. So this here also what happens? This bromoethane, it reacts with ammonia. Then we have this ethylamine plus HBr. H from the 1H of ammonia. This is your NH3. Nitrogen will have lone pairs, right? It will attack this at this carbon atom, and this bromine will leave. So we have, and nitrogen can form how many bonds? 3 bonds. Okay. So it can form 3 bonds, 1 with carbon, 2 with hydrogen. 1 hydrogen reacts with this bromine to form HBr. Nitrogen atomic number is 7, 2, 5. That means it can form 3 bonds.
I'm done. I'm done.
Okay. So here the nucleophile is in this reaction, nucleophile is ammonia molecule. The organic product is ethylamine. It is a primary amine. Primary amine, why it is a primary amine? Because if you draw the distillate formula, it is CH3, CH2, NH2. So the carbon atom which is attached to this amine group, it is further connected with only one carbon atom. So that's why it is a 1 degree amine or the primary amine. So as the nitrogen atom is attached to the one alkyl group, so it is a primary amine. If the ammonia is not in excess, we get a mixture of amine products. Here we have taken the ammonia in excess, but if it is not in excess, so we get a mixture of amine products. Why? Because the primary amine product will act as a nucleophile itself and will attack halogenoalkane molecules, forming secondary amines and so on. Because in primary amine also, in CH3, CH2, NH2 also, we have nitrogen. It have lone pair. Okay, it will attack again to this halogenoalkane bromoethane molecule, and we get a mixture of amines, secondary amines, and so on. The secondary amine formed above would be this CH3.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
NH, sorry, CH3, CH2, NH, CH2, CH3. So this is my secondary amine. Why this is secondary amine? Because this carbon atom which is attached to this nitrogen, it is attached to 2 carbon atoms. That is why it is your secondary amine. And here this nitrogen atom, this carbon atom, it is connected to only 1 carbon atom, so it is a primary amine. So you have to remember that if it is taken in excess, then the product is only primary amine. But if it is not in excess, then the products are mixtures of amines.
I'm done.
I'm done.
So write down your homework questions. Why can ammonia and amine molecules act as nucleophiles? When ammonia is reacted with an excess of halogen or alkane, mixture of amines can be formed. If we start with an excess of 1 bromopropane, give the structural formula and name of the tertiary amine which is formed. So write down. Done.
Done.
Yes.
This is a mechanism of nucleophilic substitution in halogenoalkanes. So here we have a halogenoalkane. As you know that the carbon halogen bond is polarized because of the higher electronegativity of this halogen atom. So it have a partial negative charge and the carbon have a partial positive charge. Then the halogen atom, it is replaced by the nucleophile in the substitution. Substitution means that another atom, another element would come. It would kick the existing atom. This means your substitution reaction. So there are 2 possible mechanisms that can operate in the nucleophilic substitution reactions of halogenoalkanes. Okay, so we will study SN1 mechanism, substitution, unimolecular nucleophilic substitution, and SN2, bimolecular nucleophilic substitution. Okay, so it depends on the structure of halogenoalkane involved in the reaction. So we will see the SN2 mechanisms and SN1 mechanisms. So write it down. So first we'll study nucleophilic substitution, which is bimolecular, that is SN2. So 2 means bimolecular, N means nucleophilic, and S means substitution. Okay, so this is for primary halogenoalkanes. That means in this SN2 mechanism, the rate of reactivity is greater for primary, then secondary, and then tertiary. In primary halogenoalkanes, it containing only 1 halogen atom. It is bonded to a carbon atom, which is itself bonded to one other carbon atom and 2 hydrogen atoms. So this is your 1 degree halogenoalkane. This means that the carbon atom bonded to the halogen, the carbon atom which is bonded to the halogen, it is attached to only 1 alkyl group. Okay, it is attached to only 1 alkyl group and 2 hydrogens. For example, 1 chloropropane. If you want to draw 1 chloropropane, it is CH3, CH2, CH2, Cl. Okay, so this carbon which is attached to halogen, it is connected to only 1 carbon atom. It is a primary halogenoalkane. In this case, carbon atom bonded to chlorine atom is attached to only 1 alkyl group and ethyl group. Okay, so rate you have to remember for SN2 reaction 1 degree, then 2 degree, and then 3 degree. So write it down, then we'll see the mechanism.
I'm done.
You now see the mechanism here. This is my 1 degree halogenoalkane, 1 degree bromoethane, because this carbon which is attached to halogen, it is connected to only one carbon, so it is 1 degree halogenoalkane in which SN2 reaction can easily occur. So this is my nucleophile. OH minus is nucleophile. It attacks this carbon and this bromine leaves. So we are doing this thing only, that it attacks this carbon positive charge and this bromine will leave. Why it is attacking the carbon? You know, it is nucleophile. It is electrophilic center, right? So why it is electrophilic center? Because bromine is more electronegative. It is pulling electron towards itself. That's why it become electropositive, a carbon atom. So we have a intermediate which is formed here as COH bond is forming and the CBr is breaking. So this we have shown as a dotted line, that OH is coming and Br is leaving. Okay, you can see carbon have 5 bonds, 1, 2, 3, 4, 1, 2, 3, 4, 5. This is not possible. Okay, so what happens? The leaving group will leave and the OH will come at its position. So this is your SN2 mechanism of this is the mechanism of SN2 in primary halogenoalkane. Clear? So in this reaction, only intermediate forms, and it is a one-step reaction. One-step reaction means that nucleophile is approaching and at the same time leaving group is leaving. So it is a one-step reaction. The OH minus donates a pair of electrons to the partial positive carbon atom, forming a new covalent bond, and at the same time CBr bond is breaking. So bromine atom takes both the electrons in the bond. This is an example of heterolytic fission of a covalent bond, and the bromine leaves the halogenoalkane as a bromide ion.